Okay, hey folks, for this next learning goal, we are going to get into reaction mechanisms, and we're going to start very simple by looking at a two-step first order mechanism. Okay, so let's get our mechanism put together, and then we'll go through what some of these definitions are. So in this first mechanism we're going to look at, we're going to do this generically. We'll start with reactant A. And reactant A forms some intermediate I with rate constant Ki. After that, the intermediate is it's unstable, so it goes on to form our final product with rate constant Kp. And if we add up all of the steps in our mechanism, it looks like A just goes to product P occurring at some overall rate constant K. And what's important to note here in our observed reaction, so let's put some things down. So this is our mechanism, and this would be our observed overall reaction. We don't know the order of A in this observed overall reaction because we don't have the full details of this mechanism yet. Okay. So now looking through some of these definitions, each of these steps in our mechanism we would call an elementary reaction. Okay, and in this simple mechanism we have two. And the molecularity of our elementary reaction is the number of molecules coming together to react in that elementary reaction. So we would call a unimolecular reaction a first order elementary reaction. A bimolecular reaction would be a second order elementary reaction. And beyond that, third order or more, we call termolecular. So in these elementary steps, we can look at the stoichiometry and get the order. So for example, this first step, we see only A is involved. That would be unimolecular and first order. And we can see here in the second step, only I is involved. So that would be a unimolecular first order reaction. But we still don't know the overall order of this reaction until we know which one of these is rate determining. So let's suppose that Kp is much, much greater than Ki. So in other words, this bottom step, the last step, is fast, and the first step is slow. So what that tells us then, the first step is rate determining. Slow step is rate determining. And so what that means is our rate is equal to Ki times A. And because that's a first order step, our observed order in this reaction would be first order in A, because A is rate limiting, or because really the first step is rate limiting. It's important to note, however, if we had a complex mechanism, so maybe 2 or 3 steps, and perhaps some of those steps were first order, some of those steps were second order, the slowest step is going to be the step that gives us our overall observed reaction order. And in a simple mechanism, it can often be easy to deduce which one is slow. For example, if this is like an unstable intermediate, then it seems reasonable that this would be the slow step, and that intermediate would quickly then move on to products. But in a more complex mechanism, that's not as well known. So let's go through the mathematics of this simple mechanism. Okay. So again, we established A goes to I with rate constant Ki, and I goes to Kp with rate constant Kp. And now let's suppose that Ki and Kp are roughly equal. So now it's not totally clear which one of these is rate determining, nor is it clear how will that contribute to our rate constant. So we've got to go through and look at each individual rate law of the elementary steps. And we can do that with the following. So we're going to write dA by dt. We're going to write all of these rates as positive quantities, and we're going to push the negative sign from the relative rate, right, over to the right-hand side. So we can see this first step, dA by dt, that's a loss of A. So I'm going to put the negative sign there, and that's going to be rate constant times reactant. And because these are elementary steps, we know that this is a first order. And furthermore, we've already solved this situation, so we can already write the integrated rate law for A as the first order decay. Okay, beautiful. So now we need to write the rate law for the intermediate I, and there's two steps. One step is a decay, one step is a production. So we need to use that negative sign carefully. So in this first step, this is a positive rate. So that's a positive Ki, and it's still times A. Remember, it's rate constant times reactant. So the rates of these are the same, just opposite in sign. But now I is also involved in another reaction. And in this reaction, it's a loss. So that's going to be a negative sign, and that's Kp times I. Now here's what often can become challenging with this. This intermediate, because perhaps it's unstable, something we have a hard time measuring, we're going to be really hard pressed to determine the concentration of our intermediate if it's some unstable molecule. All the same, what we can also do in this expression is plug this in right here, which will make our expression more complicated, but that will be a benefit to us later on down the line. So I'm going to write that as A initial e to the negative Ki t minus Kp times I. Okay, so now we can write the rate of our product, dP by dt. And it's, oops, I wrote I goes to Kp. Maybe you guys noticed that like several minutes ago when we're thinking, what the heck? Okay, there it is. I goes to product. So now the product is only involved in one reaction, and it's a positive rate. And remember, it's still always going to be rate constant. I can't talk and write at the same time. It's going to be rate constant times reactant. So that's going to be Kp times I. Okay. So now, rearranging this expression for the intermediate, we would see that it takes on the form of a differential equation. So I'm going to note that if we were to do some algebraic rearrangements here, we come up with the following. di by dt plus Kp times I equals Ki times A naught e to the negative Ki t. And I'll write this in a more generic way. So I'll write that as dx by dt plus some constant A times x, so remember I is our x here, equals B e to the negative B t. Okay, so this is a standard diffie-q, standard differential equation that has a known result. So I'm just going to go to that result directly and write down the following. So I, and I'm going to put the little t there just to note that that's I at any time t, will be equal to the following. So this is the standard solution to that differential equation. It goes Ki over Kp plus Ki times the quantity e to the negative Kit minus e to the quantity negative Kpt, end bracket, all times A initial. And I'm going to box that off. And what we should note here is this is now a complicated expression for our intermediate, right? This is not a simple, straightforward, like first order, second order situation. And then furthermore, plugging in the solution for our product, right? We just noted that it's Kp times that iodine concentration. So we're going to get an even more complicated result. And I'm just going to write it down directly. And this is already doing some of the algebra. So that ends up with Ki times E to the negative Kpt minus Kp E to the negative Kit. So I'm not too worried about you being able to derive this. I'm just writing the result down to be complete. And so that we can appreciate that it is a rather complicated expression, right? And then it's all times the concentration of A. So we get these two rather really complicated looking results for just a very simple mechanism. And that simple mechanism is in the case where there's no clear rate determining step. So let's see what something like that looks like on my Mathematica file. So I've got this same mechanism set up here. And now the way that I've set this up for my demo, I know I should be consistent with my lettering, but it goes A goes to B, and then B goes to C. So that's how I have that set up here. So first I'm going to put some A molecules in there. And we can see my C and B molecules are at 0 because I haven't allowed them to react. And now I'm going to turn on K1. And when I turn on K1, you can see A forms B in this first order rate. But because I haven't turned K2 on, no product has formed. But now if I form some K2, you can see as I'm turning K2 on, product C is forming and intermediate B is decaying. And now we'll go right to this situation here where K1 and K2 are roughly equal. And you can see here the intermediate, right? That's this complex rate law that we're getting where it goes to a maximum. And you can see that maximum corresponds to when they're all equal to each other. So we could think of that as something like analogous to an isobestic point or something like that, right? So there I can kind of scale them nicely there so they're all intersecting. And now this product also is taking on a rather complicated looking rate law. What's important to note, however, is A is still decaying in its regular old first order pattern. So nothing too complicated has happened with A. But in this simple mechanism, right, with no clear rate determining step, the kinetics for our intermediate and the kinetics for our product get complicated. Okay, we'll continue on with this in the next video.